Chapter 4 next, on number theory and cryptography. And the first section looks at divisibility and modular arithmetic. So yeah, the operation we're focusing on is division. Okay, yeah, we're all familiar with division. It's easy to do on your calculator, so yeah, 27 divided by 3, that equals 9. What does it mean? Yeah, it means 3 fits into 27 9 times. 11 fits into 11 once, so 11 divided by 11 is 1. If you try this on your calculator, 61 divided by 7, you'll get a decimal. So why is this one a decimal? Well, yeah, so now the 7 doesn't fit in evenly. It does fit in 8 times, but there's something left over. Alright, if you remember long division, so here we have 61 divided by 7, or 7 into 61. So as a long division, doing it by hand, yes, 7 goes into 61. The best you can do is 8 times. And if you subtract that, so 7 times 8 is 56. Subtract, that's 5. So there's 5 left over. That's called the remainder. And the number of times it fit in, that's the quotient. Okay, so for these first ones, the quotient, so dividing 27 by 3, the quotient is 9, and the remainder is 0, so nothing left over. Here the quotient was 1, and the remainder was 0. But for 61 divided by 7, the quotient is 8, and the remainder is 5. Okay, so in words, 7 fits into 61 8 times, with a remainder of 5, so 5 left over. Okay, we have a notation for this, so, well, yeah, also words. So we say 3 divides 27. Okay, so that means 3 divides evenly into 27 with no remainder. 11 divides 11, but 7 does not divide 61. Doesn't go in evenly. Alright, so that's what divides means in this context. And we write it with a vertical line. So this says 3 divides 27, 11 divides 11, and then if you put a bar through it, that means 7 does not divide 61. Alright, so example 1, are these true? Does 9 divide 206? And does 7 divide 217? Alright, so for that first one, yeah, let's divide 206 by 9. So doing it like this, yes, so 9 goes into 20 2 times, put the 2 over the 0. 2 times 9 is 18. Subtract, so 20 minus 18 is 2. Bring down the 6. Alright, yes, I'm doing these with my other class. Then 9 into 26 goes 2 times. 2 times 9 is 18, subtract, that's 8. Alright, so 9 goes into 206 22 times, but there's 8 left over. So since the remainder is not 0, that means that 9 does not divide 206, or you could say 9 dividing 206 is false. Okay, so to divide we need a 0 remainder. And yes, so for the other one, yes, 7 goes into 217 31 times exactly with a 0 remainder. So the second one is true. Okay, yeah, another way to think about this, this is saying 7 is a factor of 217. So 217 is 7 times 31. All right, so for every division, there's a multiplication. So in general, for any two integers a and b, with a not equal to 0, then a divides b is also the same as saying a is a factor of b. Or turn that around, b is a multiple of a. And a multiple, that just means b is equal to a times c for some integer c. Alright, so a divides b, and so a is a factor of b. Here's a confusing one. Example 2. Is this true? So does 17 divide 0? Yeah, think about it. Is 17 a factor of 0? Is 0 a multiple of 17? Is 0 equal to something equal to 17 times something? So the answer to all of these is yes. So yes, 17 does divide 0. It goes in exactly 0 times with no remainder. You can write it like this. So 17 times 0 is equal to 0. Okay, so 17 is a factor of 0. And yeah, there's nothing special about 17, so every non-zero integer divides 0. Okay, next, the division algorithm. Okay, so let's talk more about remainders. So if you divide an integer by 9, for example, what are the possible remainders? Yeah, we already saw in example 1, if you divide 206 by 9, the remainder is 8. Could there be a bigger remainder? No, so remainders can't get too big. So if you have a remainder of 9, for example, then you made a mistake because 9 fits in one more time. Okay, so the biggest, if you divide by 9, the biggest the remainder can be is 8. So for any integer divided by 9, the remainder has to be one of these numbers. And in our example, yet 206 divided by 9 was equal to 22. That was the quotient. The remainder 8. And we can turn that around. Yes, so 206 is equal to 9 times 22. So yeah, we're dividing by 9, so that 9 is called the divisor. So it's 9 times 22, and the 8 was left over. That's the remainder. And yeah, this 22, that's the quotient. Yeah, there's a name for the 206 as well. That's the dividend. Okay, so yeah, so 9. So 206 divided by 9 goes in 22 times, but with 8 left over. Yeah, if you remember mixed numbers, yeah, you could write this 206 over 9. The improper fraction, it's equal to 22 and 8/9. Another way to think of it. Okay, yeah, just remember the quotient. That's the number that comes out on top, and the remainder is this guy. Okay, so we have this example, and then the general case is covered by this division algorithm. Yeah, it's not really an algorithm like we've seen. It's really a fundamental theorem. So it says for a, any integer, and d, a positive integer, then there are unique integers q and r, so that a is equal to d times q plus r, and r is in this range. R is between 0 and, so strictly less than d, so it's between 0 and d minus 1. Okay, so start with any integer a. It could be negative or positive. We're dividing it by d, and we're getting a quotient q and remainder r. Okay, the remainder r is between 0 and d minus 1. So like we saw in this example, the remainder can't be as big as d. All right, so this is kind of abstractly giving the the properties of quotients and remainders. But yeah, all we're doing is dividing and looking for the remainder. Example 3, find the quotient q and remainder r when 218 is divided by 3. Well, right away we know that the remainder, if we're dividing by 3, the remainder is a number, it's either 0, 1, or 2. Let's see which is it. So I'm doing the division here. So 218 divided by 3. 3. So doing this part first, so 3 goes into 21 7 times. 7 times 3 is 21, subtract, that's 0, bring down the 8. 3 into 8 goes, the best you can do is twice. 2 times 3 is 6, subtract, the remainder is 2. Okay, so if you did get a remainder bigger than 3 or bigger, then you made a mistake. Okay, so the quotient, that's 72, and the remainder is 2. And we can write it like this. So yeah, 218 is equal to the divisor times the quotient plus the remainder. Alright, yeah, so nothing difficult. Yeah, this is just what I'm doing with my Math 01 class. Alright, so here we have A divided by D. Quotient Q. So yeah, we can use this notation for the quotient. A div D. Okay, so A divided by D, the quotient is Q. I'm going to use this notation. And for the remainder, we can use this, A mod R, A mod D, equal to the remainder R. Yeah, div, short for divides or division. Mod, that's a new word, that's short for modulo. Coming from the Latin for measuring. Okay, so 218 div 3 is that quotient 72, and 218 mod 3 is the remainder 2. Okay, so just highlighting this new notation. Okay, yep, so division. Yeah, we've skipped some properties here, yeah, just to mention them. So if A divides B and A divides C, then A divides B plus C. Okay, that's not too hard to show. Also, if A divides B and A divides, or if A divides B, then A divides BC for any integer C. And if A divides B and B divides C, then A divides C. Alright, so yeah, we have these properties of divides. Okay, the division algorithm again, and here's the notation. Example 3, what are the quotient and remainder when 101 is divided by 11? Oh, well, 11 goes into 101. The best you can do is 9 times. That's 99. And 2 left over. So 101 div 11 is 9. That's the quotient. And 101 mod 11 is 2. Example 4, yeah, how about with a negative A? So what are the quotient and remainder when negative 11 is divided by 3? Okay, so this time the different ways to do it. The key thing is you need the remainder has to be, if you're dividing by 3, the remainder has to be either 0, 1, or 2. So this is the right quotient to use negative 4. Okay, so A is equal to D times Q plus R. Okay, so the only choice for Q that has R in the right range is negative 4. Okay, so the division algorithm is saying that Q and R exist and they're unique. Okay, so yeah, for negative A, then yeah, maybe some playing around to get the right Q and R. Okay, so yeah, following the book again, this next subsection, modular arithmetic. And yeah, it's also called clock arithmetic. Maybe simplest to see on the 24-hour clock. So military time. I suppose it's 9 hours on a 24-hour clock, so that's 9 a.m. What time will it be in 100 hours? Okay, so it's 9 o'clock now. If you add on 100 hours, what time will it be? Well, since the time goes back to 0 every 24 hours, we only need the remainder after dividing by 24. Okay, so take the 9, add on the 100. So we have 109 hours, and if you divide that by 24, okay, so think of the hands on the clock going round and round. We add on 100 hours, they go round and round, but every 24 it's back to 0, so we can just divide by 24 and see what's left. 24 goes into 109. Yeah, the best you can do is 4 times, that's 96. I'll subtract, and the remainder is 13. Alright, so we're 4 days later, but the time on the clock is 13 hours, 1 p.m. Alright, so that's this idea of, yeah, if you just care about the time, then yeah, you just need the remainder. We didn't need to know it was 4 days later. Yeah, maybe a simpler way to do this question, yeah, just focus on the 100 hours. If you look at 100 mod 24, so divide 100 by 24, you get remainder 4. Okay, so adding 100 hours is really the same as adding 4 hours on the 24-hour clock. So 9 plus 4 is 13 again. Okay, so the point in this kind of clock arithmetic is, we only care about the remainders. We don't care about the quotient or the original number 100, really. Let's set up some notation. So in this example, we're dividing by 24, and that 24 is called the modulus. Okay, and for times on this clock, we only need the remainder after dividing by the modulus. If two integers a and b represent the same time, then we can write it in this notation and say a is congruent to b modulo m. Here m is, the modulus is 24. Okay, so for example, here 100 is congruent to 4 modulo 24. They represent the same time. Okay, so we're using this new notation. We've already seen this word mod. We're using it slightly differently here in parentheses. And we have this congruent or congruence notation, so it's like equality but with three bars. Okay, so what's the general definition for this? So let A and B be integers, and M any positive integer. Then A is congruent to B mod M, modulo M. What does that mean? It means M divides the difference A minus B. So that's the key idea we need for modular arithmetic. So two numbers are congruent. Mod M means M divides the difference of those two numbers. Okay, that's what I'm trying to explain here. So two numbers represent the same time. If 24 divides the difference, then the two times are a certain number of days apart, but you've got the same time showing up on the 24-hour clock. So just getting used to this. Example 4, show that 253 is congruent to 169 mod 7. Okay, so matching it up, so A is 253, B is 169, M, the modulus, is 7. So we want to check that this is true. So the difference, A minus B, is 84. So does 7 divide 84? Yes, that's true. So 7 goes into 84 evenly with no remainder. So 7 divides 84 is true. So that means this is true. Okay, so 253 is congruent to 169 mod 7. So 7 does divide the difference. Okay, in other words, the difference is a multiple of 7. Example 5 in the book. Determine whether 17 is congruent to 5 modulo 6. Let's do that first. Well, look at the difference. 17 minus 5, that's 12. Does 6 divide 12? Yep, goes in exactly 2 times, so this one's true. Okay, so 17 is congruent to 5 mod 6. How about these two? Is 24 congruent to 14 mod 6? Well, no, so now the difference is 10, and 6 does not divide 10. Yeah, another way to say it, 10 is not divisible by 6. So 6 goes into 10 once, but the remainder is 4. So 24 is not congruent to 14 mod 6. And yeah, so you can use, so for not congruent, just put a line through it. Yeah, this is the guy, Carl Friedrich Gauss. Yeah, one of the most famous mathematicians. And yeah, he developed this whole theory, took it a long way, this modular arithmetic. All right, yeah, let's say a bit more about this A congruent to B mod M idea. This notation, this congruence notation, is similar to equality, and it's meant to indicate that there's something the same about these two numbers, 253 and 167. So what's the same about them? What do they have in common? Well, the simple answer is they have the same remainder when you divide by the modulus 7. So that's what's the same about them. 7 goes into 253 a certain number of times, and the remainder is 1. And for 169, when you divide by 7, the remainder is also 1. Remember our remainder notation. Okay, so in general, A is congruent to B mod M if and only if A mod M is equal to B mod M. So the remainder when you divide A by M is equal to the remainder when you divide B by M. Alright, yeah, is this getting confusing? So we're saying, so if you fix a modulus M, we're saying two numbers are the same, they're congruent, if and only if they have the same remainder when you divide by M. Okay, so this modular arithmetic is really, it's focusing on the remainders and kind of ignoring the original numbers and the quotients. Example 5, find 101 mod 3 and 208 mod 3. Use these results to decide if 101 is congruent to 208 modulo 3. Okay, so let's find 101 mod 3. So that just means the remainder when you divide 101 by 3. So 3 goes into 10 3 times. That's 9. Subtract, you get 1. Bring down the 1. 3 goes into 11 3 times. Subtract the 9, you get 2. So the remainder is 2. So 101 mod 3 is equal to 2. About 208 mod 3. Okay, doing the calculation here. 3 goes in 69 times, but 1 left over. The remainder is 1. Okay, we got a different remainder. Well, 101 is congruent to 208 mod 3 if and only if we get the same remainder. So that means these two numbers are not congruent mod 3. Okay, so 101 is not congruent to 208 mod 3. We could have done this more directly, so just see if 3 divides the difference. Okay, it's not going to divide the difference, but this is another way to check it. So we're just kind of illustrating this idea. Two numbers are congruent mod M, if and only if they have the same remainder when you divide by M. All right, yeah, we'll see lots of applications of this in the next section 4.5. Just to say a bit more. So these remainders, you can base a whole kind of a theory, an arithmetic theory, just talking about remainders. For example here, theorem 5, if A is congruent to B mod M, and C is congruent to D mod M, then the sums are congruent, so A plus C is congruent to B plus D mod M, and also the products are congruent. A times C is congruent to BD mod M. Alright, so this idea of congruence, it respects addition and multiplication. So in this modular arithmetic, yeah, you can basically just work with remainders and you get a consistent kind of arithmetic. Alright, so that'll do it for this section.